Hi students, in this video I would like to discuss about P, NP, NP complete and NP hard problems. These are actually classification of various problems in computer science. So we will look one by one. So first one is P. Problems which can be solved in polynomial time is generally comes under class P. For example, linear search whose complexity is O of n, binary search log n, bubble sort O of n square, merge sort O of n log n. These types of problem comes under class P. Generally saying, problems with complexity n raised to k are considered as class P problems. So another definition is P is a set of problems that can be solved by deterministic Turing machine in polynomial time. The concept of deterministic Turing machine you already studied in the previous semesters. So another definition is problems which can be solved in polynomial time by deterministic algorithms. In the previous semesters you have studied if a problem can be solved by a Turing machine, it can also be solved by computer. So here the term deterministic will be clear when you study what is non-deterministic algorithms. So next is a class of problems called NP. Problems which can't be solved in polynomial time by deterministic algorithms. Generally comes under NP problems. Two examples are traveling salesman problem and bin packing. These two problems we will study in detail later. Problems which can be solved in polynomial time by non-deterministic algorithms. Those algorithms are also known as lucky algorithms. Such problems are called NP problems. So here the solution can be solved in polynomial time, but we are using non-deterministic algorithms. So you look at the state diagram. Here we have three states Q1, Q2 and Q3. After Q1 you can either go to Q3 or Q2. But actually we have to choose any one of the path, either Q2 or Q3. This is called non-determinism. We are not sure about where to go from Q1. Either we can go to Q2 or Q3. Sometimes we will get the correct solution if we go to Q2, or in some other cases we will get the correct solution if we go from Q1 to Q3. So it is something similar to the non-deterministic Turing machines. So next point is the class NP consists of those problems that are verifiable in polynomial time. So the term verifiable means for a given solution of a problem, we can check that whether the solution is correct or not in polynomial time. Here we can solve the problem in polynomial time by using non-deterministic algorithm. These problems can be verified in polynomial time. That means for a given solution of a problem, we can check that whether the solution is correct or not in polynomial time. So when a solution is verified, it has two possible answers, yes or no. Next we are going to discuss a term called decision algorithm. A decision problem is a question that has two possible answers, yes or no. So here actually we are verifying the solution of some problem. So for verifying we have to run some algorithm. Such algorithms are called decision algorithm. So any problem which will give answers either yes or no can be considered as decision problem. To solve that problem we are running some decision algorithms. So NP problems are verified using decision algorithm in polynomial time. So one more definition of NP. NP is a set of problems that can be solved by non-deterministic Turing machine in polynomial time. Okay, next you look at this Venn diagram. From the diagram it is clear that P is a subset of NP because deterministic algorithms can be considered as a special type of non-deterministic algorithm. Next we are going to study two types of problem, decision problems and optimization problems. Many problems of interest are optimization problems in which each feasible solution has an associated value and we wish to find a feasible solution with the best value. So optimization problems always give some solution or value. So in some case we will look for the minimum value. In some other case we will look for the maximum value. So for example, for a parameter execution time of a program in a computer, we always look to minimize the execution time. Suppose if we are designing a computer and we want to add some storage space, we will always try to add maximum storage space. Optimization problems always will be either minimizing or maximizing the value. So always remember the output will be a value. So next point, for example, in a problem that we call shortest path, we are given a graph G and vertices U and V, and we wish to find a path from U to V that uses the fewest edges. In other words, shortest path is the single pair shortest path problem in an unweighted undirected graph. So here there's a problem called shortest path where there will be a graph and we have two vertices. Here we want to find the path from U to V but using fewest edges. That means here we are minimizing the number of vertices in the path between U and V. So the shortest path we can call it as a optimization problem. So a decision problem is a question that has two possible answers, yes or no. So that we already discussed. For example, a decision problem related to shortest path is path. So here shortest path is an optimization problem. For this optimization problem, we have a decision problem called path. That means given a directed graph G, so here we have a graph G, here we have vertices U and V and an integer K. So the question is, does a path exist from U to V consisting of at most K edges? So shortest path have 3 inputs, G, U and V. Here path will have 4 inputs, G, U, V and K. So here we are checking whether the value of K is the shortest path from U to V. That means value K is the minimum number of vertices in the path from U to V. So that problem path is a decision problem because it is checking whether the output of shortest path is correct or not. So we usually can cast a given optimization problem as a related decision problem by imposing a bound on the value to be optimized. So this point can be explained with the help of our earlier example. We can solve path by solving shortest path and then comparing the number of edges in the shortest path found to be the value of the decision problem parameter K. So here shortest path is an optimization problem which will give an output. So let it output be K. Using the problem path we can verify whether the output generated by shortest path is correct or not. So in the previous slide for NP problems we already discussed it is using non-deterministic algorithm. So sometime it may give correct output, some other time it may not give correct output. So for an optimization problem, if we have an additional decision problem also, we can check whether that output generated by optimization problem is correct or not. So from this slide you have to understand there is a relation between optimization problem and decision problem. We usually can cast a given optimization problem as a related decision problem. That means we can convert or we can cast a given optimization problem to a related decision problem. Next we have to study a concept called reduction or transformation. Let L1 and L2 are two decision problems. We already discussed about decision problems. Suppose algorithm A2 solves L2. So to solve any decision problem we need some decision algorithm. To solve the decision problem L2 we are using algorithm A2. That is, if Y is an input for L2 then algorithm A2 will give answer yes or no depending on whether Y belongs to L2 or not. The idea is to find a transformation from L1 to L2 so that algorithm A2 can be the part of an algorithm A1 to solve L1. Because here we have an algorithm A2 to solve L2. So here we have an algorithm A2 to solve L2. Similarly, we have to design some algorithm A1 to solve L1. So here what we are doing is we are trying to make L2 as a part of L1. L2 as a part of L1 because we didn't have any A1 algorithm. Here what we are going to do is here we are trying to incorporate algorithm A2 in A1. So A2 becomes a part of algorithm A1. If there exists a polynomial transformation from L1 to L2, then we say L1 is reducible to L2. If we can transform algorithm A2 to A1 in polynomial type, then we can say L1 is reducible to L2. So here what you have to understand is reducibility. When we can say L1 is reducible to L2. So you just look at the diagram. Here I have L2, an algorithm for L2 that is A2. Some input will be given. It will generate yes or no. Similarly, we have an algorithm L1 to solve a decision problem. But actually L2 is part of L1. It is L1 contains L2. So if we can do this transformation in polynomial time, we can say L1 is reducible to L2. L1 is itself a decision problem. That's why its output is yes or no. Inside L1, we actually have algorithm for L2. So next is definition for NP complete and NP hard. A decision problem L is NP complete if L is NP. Every problem in NP is reducible to L in polynomial time. So we already studied what is decision problem. We already studied what is reducibility. Those two concepts are applicable in definition of NP complete. So we have a problem called L. When we can say it is NP complete, the problem L must be under NP, and each problem in NP is reducible to L in polynomial time. So already there are some problems, or there are a number of problems in NP. If we can reduce all those problems to L in polynomial time, we can say problem L as NP complete. So reducible to L in polynomial time we discussed in the previous slide. So a problem is NP hard if it follows property 2 mentioned above, doesn't need to follow property 1. So here I have a problem L. It need not be an NP problem, but if all NP problems are reducible to L in polynomial time, we can say such problems as NP hard. Another definition of NP complete: a decision problem is NP complete if L is NP and NP hard. If it follows property 2, we can say NP hard. So if it follows properties 1 and 2, that is, here 1 is written as L is NP, and instead of this statement, here written it as NP hard. So this is just another definition of NP complete problem. This is the Bern chart which shows the relation between PNP, NP complete and NP hard. So next is how to prove NP completeness. We already studied NP complete problems must satisfy two conditions. The problem must be NP, and all NP problems must be polynomial reducible to our given problem. So from the definition, it is almost impossible to prove a problem L as NP complete, because we want to find the polynomial reduction of all other NP problem to the given problem. That is almost impossible. So the idea is to take a non-NP problem and reduce it to L. So if there is any non-NP problem, that means that problem is proved by reducing all other NP problems to that particular problem. So if we can find a polynomial reduction from that particular NP problem to our problem L, we can say L as NP complete. If polynomial reduction is possible, we can prove that L is NP complete by transitivity of reduction. I hope you understood the concept of PNP, NP complete and NP hard. Thank you.